Welcome back. We've got an absolutely fantastic explainer for you today. We're going to completely deconstruct a legendary back-end technical assessment, the Toy Robot Challenge. So, right now, I want you to put on your lead engineer hat. Your mission? You need to bring a simulated toy robot to life, and it has to navigate a very strict environment based entirely on precise technical specs. It's a really brilliant exercise in logic, state management, and keeping your architecture clean. Let's get into it.
Okay, let's take a quick look at the roadmap for this mission. First, we'll cover the tabletop robot mission. Second, mastering the robot commands. Third, the golden rule, survival. Fourth, running the example scenarios. And finally, number 5, exceeding the reviewer expectations. All right, section 1, the tabletop robot mission, establishing the environment. Let's lay the groundwork.
So, picture this, a perfectly smooth, totally flat tabletop. No walls, no obstacles, nothing in the way. Just a pure, open grid. Now, to make this work, you've got to map this out, whether that's in your head or in your code, using a standard coordinate system. The origin point, R0, 0, is firmly anchored right in the extreme southwest corner. So just think of that as the absolute bottom left corner of your digital table.
Now, how big is this little universe? Well, it's strictly a 5 by 5 unit grid. That's it. Your robot's entire existence is confined right inside these boundaries. And since we're starting at 0, the maximum coordinates you'll ever hit on this grid are 4, 4. Burning these absolute boundaries into your brain is literally step 1 for nailing the logic on this challenge. Moving right along to section 2, mastering the robot commands, giving the robot life. Let's check out the control system.
The specs give us a really tight, specific set of just 5 commands. First up, we've got place. You feed it an X coordinate, a Y coordinate, and a direction to face, north, south, east, or west. This is what physically drops our little guy onto the board. Then there's move. This simply nudges the robot exactly 1 unit forward in whichever direction it's currently facing. Next, left and right. These just rotate the robot 90 degrees, anti-clockwise or clockwise. And here's the kicker. This rotation happens completely in place. It doesn't change the robot's physical X and Y coordinates at all. And finally, the report command. This basically just asks the robot to shout out its current X, Y, and facing direction.
So if we look at the whole logical life cycle of moving this robot around, it goes a little something like this. Step 1, you place the robot at a valid position. Step 2, you just start firing off your sequence of actions, right? Moving, turning left, turning right, in whatever order you want. And then step 3, you call that report command to check the final destination. Oh, and the specs also mention that this input stream can be fed from a file or it can come straight from standard input. That's totally up to you as a developer to design. All right, section 3, the golden rule, survival, avoiding destruction. Time to raise the stakes a bit.
So, your robot is totally free to cruise around anywhere on that pristine 5 by 5 surface, but there is a major catch. If it takes 1 step off the edge of that grid, it plummets to its absolute destruction. Game over. So, your prime directive here as the engineer is that any movement that would cause a fall must be completely prevented by your code. Under no circumstances can this robot be allowed to harm itself. Now, what's really interesting about this next part is the state management they expect from you. Honestly, this is a massive point of failure for a lot of candidates. Think about the before state. Before a valid place command actually executes successfully, your app has to just discard and ignore every other command. I mean, you can't exactly move a robot that isn't even on the table yet, right? But then, look at the after state. Once that very first valid place command happens, boom, the robot is officially active. From that moment on, any sequence of commands is fair game, including just picking the robot up and using a brand new place command to drop it somewhere else. And this really hits the nail on the head when it comes to the nuance of that survival role. Picture this. Your robot is teetering on the northernmost edge, facing north. The user sends a move command. Obviously, that's an invalid move. It's going to fall off the edge. So your program has to step in, prevent the movement, and completely ignore that command. But here is the crucial part. Just because you blocked 1 bad command, the robot doesn't just shut down and give up. It has to keep listening. So if the very next command is something safe, like asking it to turn left, your code still has to accept and execute that. The robot just ignores the dangerous instruction and waits patiently for a good one. Okay, section 4, running the example scenarios, proving the logic. Let's actually walk through the simulated test runs from the technical brief. Here's the very first, most basic test.
The input sequence tells us to place the robot at 0, 0, facing north. Remember, that's our bottom left corner. Next, we fire off a move command. Since it's facing north, it takes one step up the y-axis. So when we hit report, the expected output is 0, 1, north. It's simple, it's straightforward, and it perfectly tests your basic placement and forward progression.
Now, let's check out this second scenario. This one is all about testing rotation in total isolation. Once again, we place the robot at 0, 0, facing north. But this time, the command is left. And like we talked about earlier, rotation doesn't change where the robot physically sits. It just pivots 90 degrees anti-clockwise. So when we run report, our X and Y are still 0, 0, but our facing direction has successfully flipped from north to west.
All right, let's look at the final example and watch how this all comes together into a fully chained sequence. We place the robot at 1, 2, facing east. We move forward 1 unit, so X bumps up to 2. We move again, X bumps up to 3. So now we're sitting at 3, 2, east. Next, we tell it to turn left. The robot stays right at 3, 2, but pivots to face north. Finally, we drop one last move command, which nudges our Y coordinate up by 1. We hit report, and it flawlessly maps to our final destination, 3, 3, north. Listen, if your code can spit this out correctly, you know for sure your core logic is rock solid. Which brings us to our final section, Section 5, Exceeding the Reviewer Expectations, the Hidden Test. Let's talk about what's really going on here. Getting the robot to move around is honestly only half the battle. I really want to draw your attention to this direct quote right from the spec doc. Keep it simple, keep it dry, but don't overcomplicate or over-engineer. Comment and test as appropriate. This right here is the reviewer's absolute mantra. By the way, dry just means don't repeat yourself. See, they aren't just hunting for a script that prints out the right coordinates. They're looking closely at how you solve problems and how you architect your code. They want clean, they want readable, they want well-structured. And to that end, to truly pass this challenge, there are some really specific non-coding deliverables they expect from you. First, you've got to provide your test data and results. Actually prove your logic works programmatically. You need to write some clear comments that explain your thought process. You absolutely must include a solid README file with exact instructions on how to actually run your project. And this is huge. The brief specifically tells you not to spend days and days agonizing over this task. Instead, they want you to leave notes detailing what's missing or what you might architect differently if you had more time. Honestly, doing that shows incredible self-awareness and shows you know how to prioritize. Oh, and there is one absolute zero compromise directive stated right in the brief. Please do not copy solutions existing off the internet. Look, this is a really famous challenge. Are there hundreds of solutions sitting on GitHub right now? Obviously. But copying them entirely defeats the purpose. This is your chance to showcase your own engineering chops and your own unique flavor of problem solving. So that leaves us with one final big question. You know the environment now, you know the commands, you know the constraints, and you know exactly what the reviewers are digging for in your code. So, how will you architect your robot's survival? Are you going to lean into an object-oriented approach, maybe functional programming, or how about building out a really robust state machine? I highly, highly encourage you to pop open your code editor right now, spin up a new file, and just write out your very first place command. Thanks so much for hanging out with me for this explainer, and hey, happy coding!